All right, everybody, welcome back. We're in the next section now. Remember, just like we did with confidence intervals, just like we did with hypothesis testing about one mean, we start with proportion, we move on to mean. So we're going to do means. We're not even going to mess around with variances. That's a whole nother deal. However, it's basically the same thing. All we're going to do is we're going to test a null hypothesis and an alternative hypothesis. And typically, but not always, typically you will have that the mean of one population is equal to the mean of another population. And then you're either going to have the mean of one population is not equal to the mean of another, the mean of one population is greater than the mean of another, excuse me, or the mean of one population is less than the mean of another. Remember, what we're doing is we got two populations. Now, these are called independent samples, which implies that these populations have to be independent. This population is going to have its own mean. This is going to have its own mean, which we don't know. We're going to draw out a sample, just like we did before. We're going to draw out a sample here, and we're going to compare them. We're going to get X bars, etc., etc. Okay? Fair enough? Nothing to it. Now, we're going to assume that the samples are unknown, or excuse me, that the standard deviations are unknown. Okay? And all we're going to do is, just like before, we're going to write up our assumptions, pardon me, and we're also going to write up our test value. All right? Then we'll jump right into independent samples where the standard deviations of both populations are known. And I'll give you that, and then we'll do a problem together. Okay? Sound good? Excuse me, I'm getting a sip of caffeine here. Starting to flag. Okay, so our assumptions. I'm not really starting to flag. I just want caffeine. Watch out. Yeah, you'll see my writing get a little crazy. Let's see. Number one, let's see. The assumptions, of course, are always SRS. So we want simple random samples from both populations. Both pops. Maybe I am having. Look at that. It's crazy. Pardon me. Of course, the samples are independent. Samples are independent. In other words, they have no effect on each other. Dependent. Now, this is a biggie, okay? Either, whoa, they're a little crazy. Now, it's either or both, of course. You can have both if you want. So, either the first sample is greater than 30 and the second sample is greater than 30. In other words, the sample sizes are greater than 30. Or both samples are drawn from normal populations. Normal pops. If you don't have either one or the other of this, then you can't do this. You're screwed. You got to go digging for way more information. Okay, you need more data values. Okay, so that's what we got going here. Now, watch how this works. Excuse me. So simple to work with. What we're going to do is we're going to do a T. Remember, if we don't know sigmas, we always have to go with T. Now, we'll talk about degrees of freedom here in just a second. Okay, so all that we're going to do is we're going to take the mean from the first sample minus the mean from the second sample. From that, we're going to subtract the population mean, or what we suppose that it is, what we think that it is, from the first, and the population mean from the second. And remember, those always come from your null hypothesis. All right? Remember how before we talked about this? You may or you may not. There's nothing that says that I have to let the mu1 equal mu2. I could actually say that I could say something like mu1, I'm running out of space here. I'm going to erase these little alien eyeball thingy-dingies. I could actually say that mu1 minus mu2 is equal to 5. And what that says is that the difference between the population means is 5. For example, let's say that I test the miles per gallon in a Honda versus the miles per gallon in a Toyota. And I believe that the difference in miles per gallon in their top-of-the-line car is actually 5 miles to the gallon. All right, that would be an example of, instead of mean 1 equally mean 2 and us testing that, I know, I don't know if Honda's got a higher miles per gallon or if Toyota does, but let's say that I know that Honda does, and I'm trying to pin down what it is. Well, that would be an example where we say m1 minus, or mu1 minus mu2 equals 5, rather than mu1 minus mu2 equals 0. Okay? Okay, so hopefully you see that, and again, you'll get to play with that some more down the road. And this is divided by the square root of, and I take the sample standard deviation from the first sample, and I square it, and I divide it by, excuse me, n1, and I add that to the sample standard deviation from the second sample, and I square it, and I divide it by n2. Sometimes you'll hear this referred to as the pooled standard deviation. All right, where again, it's kind of beyond the scope of the mathematics for this course. All right, I just want you to see how this thing works. All right, if we're going to do a confidence interval, let's see, you can probably tell where this is going to go. You know that mu1 minus mu2 is going to live between two values, which is going to be x1 bar minus x2 bar minus the error, and then x1 bar minus x2 bar plus the error, and your error term is just equal to your t sub alpha halves, which we got lots of practice with dealing with that, and then this s1 squared over n1 plus s2 squared over n2. That's our error. It works just the same. Now, question is, what are degrees of freedom? We are going to keep it super simple. The degrees of freedom are just, all it's going to be is the smaller number. Wow, sorry about that. This caffeine is starting to kick in. Smaller of n1 minus 1 and n2 minus 1. That's it. That's all there is to it. Okay? So, not to panic, piece of cake. That's our test value. That's our confidence interval. We know how to find degrees of freedom. There's a more complicated way and a more accurate way really to find degrees of freedom, but we really don't care. Believe it or not, there's not a whole lot of difference between the two. Okay? So let's go ahead and I'll find a good problem for us to do. I'll throw that up there and I'll throw the solution. And guess what? We'll be, oh wait, you know what? I lied. Let's change the business here. What if sigma 1 and sigma 2 are known? All right? Now, hopefully you can figure this out. Remember, if I know what the parameter standard deviation is, right? If I know that, then I don't have to putz around in this t land. Remember, t is crazy. It's got a family of curves. They're not normal. It's not normal curves. They look normal, but they're not all normal curves. It's just this family of crazy curves that sort of expand for us to what would be the right word? To accommodate for accuracy and precision. All right? However, watch. If I know the standard deviations from both populations, and you may say, well, I don't know that that's terribly reasonable. Well, think about my Honda and Toyota deal. I mean, think about it. They made a lot of cars over the course. They can probably figure out what the standard deviation is, or they can create confidence intervals to do that for them. Okay. All right. So watch what happens. T turns into Z. If you know sigmas, T always turns into Z. All right. And we just end up with x1 bar minus x2 bar. Let's see, minus mu1 minus mu2. That's often 0, which is nice. It makes life easy. And then instead of those s1 squares, I've got sigma 1 squared over n1 plus sigma 2 squared over n2. And the best part is when I'm dealing with z, no df's, right? Because I get to play ball on the standard normal curve. Okay? And if you come over here, then I know, whoa, I know that the error bound for this guy is just going to be exactly the same thing, only I'm going to have a z alpha over 2 root sigma 1 squared over n1 plus sigma 2 squared over n2. All right? Now, if I'm moving too quickly, if these formulas are coming out too fast, just yell at me, pin me down in class, and we'll get it done, okay? So don't panic on that. All right? So I'm going to find a good problem for you, and we'll hop into it, okay?